Okay, here's a very simple equation with coefficients not constant, because it's x squared. It's not a constant function. So, so far, I was telling you that if you have a non-constant coefficient differential equation with homogeneous, meaning that the right side is 0, in that case, you should try to find a solution as a power series. Now, today I want to show you that this doesn't always work. And let me show you this one as an example. So, how does it work? First, let's try to solve it like the other ones. You first set y as sigma n from 0 to infinity of an x to the n. Its derivative is n an x to the n minus 1 y double prime n minus 1 an x to the n minus 2. And you put these into here. Since y prime is not here, so I don't even have to use this. Only these two get used in here. So the equation turns into I messed up one part of it. Where did I make a mistake?
Yeah,
The n minus 2. It should be 1, 2. Right? Good. All right. This now can be moved inside, and then x squared times x to the n minus 2 just becomes x to the n, which now becomes sigma n from 2 to infinity n times n minus 1 an x to the n minus sigma n from 0 to infinity of an x to the n equal to 0. That's the differential equation I get. That's the power series equation I get if I put these into the left side. Now, this one starts producing terms starting from n equal to 0. However, this starts producing terms starting n equals to 2n afterwards. So you should first figure out what happens to this one when n is 0. When n is 0, you get a0 with the minus sign. That's it. X to the 0th power is 1. If you want, you can put it here, but this is 1. So this is optional. This is just 1. That's what you get when n is 1. When n is 0. When n is 1, what do you get? a1 x to the first power. That's what you get, right? Now, starting from n equals to 2, both of these sigmas produce terms, and therefore, I can put the rest of them into a single sigma. So I have plus sigma n from 2 to infinity of n minus 1 an minus an x to the n equal to 0. That's what I get. And then I a0 minus a1x plus sigma. Now I notice that the an's are in both, so I can even factor out the an. And what I end up with is n minus 1 an x to the n equal to 0. And for a power series to equal to 0, we've learned that all the coefficients should be 0. So the implication is that a0 has to be 0, a1 has to be 0, and n times n minus 1 is n squared minus n minus 1 times an has to be 0. But when is this 0? This thing is 0 when n is equal to 1 plus minus square root of 5 over 2. Right? If you set this equal to 0 and solve it as a quadratic equation, the only time this is equal to 0 is when n is equal to negative of negative 1 plus minus square root of negative 1 squared minus 4 times 1 times negative 1 over 2 times 1. So that's like 1 plus minus square root of 5 over 2. Those are if n is either one of these values, either 1 plus radical 5 over 2 or 1 minus radical 5 over 2, then this is equal to 0, which would allow an to not be 0. But, see, n is from 2 to infinity only taking integer values. So can this be 0? No. Never. Therefore, what do you end up with? For this times that to be 0, that would only mean that
Every 0.
Every an is 0. For all n 2 or greater. See, this is from 2 to infinity, so this should happen for n 2 or greater. And we also have a0 and a1 as 0. So what's the answer that you get? If you go back and plug it in here, see our original solution, sometimes you call this the ansatz for this equation. So when you're doing this guessing game, when you're trying to guess the solution rather than solving the differential equation, sometimes you start with some kind of an ansatz. Ansatz means sentence in German. So you start with some sentence predicting that the solution of such and such should be of this form. But it looks like this ansatz failed because this really means y is equal to a0 plus a1x plus a2x squared plus a3x cubed, so on and so on. And now this result forces us to say that this is all 0. It's all 0. And so you're getting the solution as just 0 for this. Now, do you recognize that, do you realize that y equal to 0 is actually a solution to this? Right? If you have y as 0, if y is 0, that means y double prime is of course 0. Therefore, the left side is 0, so it's a solution. But such a solution is called a trivial solution. It's called a trivial solution. And the trivial solution is a solution that's already known even before solving it. And this trivial solution, of course, does not contain two free parameters. And because it doesn't contain two free parameters, we know that it's not one of these, this cannot be the general solution. Right? For us to have a general solution of a second order differential equation, I better have two free parameters, but I don't. So that's not good. So that tells us that we actually failed in getting the solution of this differential equation when we tried this. Okay. Now, the obvious question to ask is, obvious question that we would ask at this point is, why did it fail? Was there something special about this differential equation that when we approached it as a power series solution, it would fail? Well, so let me point out in what sense this is sick. Okay? It's a sick differential equation. I'm sick right now, but this is more sick. It needs some. It needs a different approach than the regular ones because the healthier ones usually you can solve it using this, but this one you can't. Now, in what sense is it totally different? Well, it's like this. See, we learned before that if you have a power series solution like this, then recall that y of 0 is the a0, and y prime of 0 is a1. Do you remember that when you have, when you set your solution as this form, then y0 is a0 and y prime 0 is a1, right? And therefore, what you're trying to say is that these are like the free parameters, right? If you're given a differential equation with two initial data for second order, then you should always be able to solve it. It is a unique solution, right? So these are like the free parameters, and you would expect a0 and a1 to be some free parameters at the end of the day when you solve this. Everything else should be expressed as something involving a0 or a1 or both. But here, when we tried to solve it like this, we were forced to have a0 as 0 and a1 as 0. So that happened, and if you go back and see what this is saying, even before trying out this solution, you can already see that y0 would be forced to be 0. Now, why is that? Well, it's really like this. Often we suppress the dependence on x, but y double prime is a function of x, and y is also a function of x, right? So these are both functions of x. And this is a functional equation, meaning that this should be true for any value of x, and including x equal to 0. So think about what would happen if you put x equal to 0. If you put x equal to 0, you would be getting 0 times y double prime of 0 minus y of 0 equal to 0. So you're forced to say y of 0 is 0. Right? Because 0 times anything is 0. So you have negative y0 equal to 0. So you're forced to say y of 0 is 0. And that's what's wrong with this differential equation. You're not free to choose your initial conditions. See, normally, the existence theorem for differential equations allows you to say, oh, if you have a differential equation, the solution always exists for any kind of initial conditions for y0 and y prime of 0. And not only that, if you specify these solutions, the solution is unique. Those are the two existential theorem and the uniqueness mathematical theorem that we were using. But somehow, this does not satisfy that. And and the reason for that is those mathematical theorems for uniqueness and existence rely on being able to cast the differential equation in the following form. If you can write down your differential equation, second order differential equation with y double prime plus px y prime plus qx y equal to 0, and if x equal to 0 does not cause any trouble, then the theorem says that for any given pair of these numbers, initial conditions, the solution exists and is unique. Okay? That's the mathematical theorem, which I refuse to prove. It's very involved, so I don't want to even discuss. By the way, if you ever want to change your major to mathematics, then you'll be learning it probably in your third year, after a gruesome semester of analysis, real analysis course. Towards the end of that course, you learn that proof. Okay? But here we're not going to discuss that proof, but we're just going to accept that. Okay? But let's just say we all know that theorem. Now let's see why this theorem doesn't apply for that case. Try to turn this equation into this form. What goes wrong? How do you turn that into this? By doing what? Notice that y double prime don't have any coefficient, right? So what should you do? You have to divide everything by x squared, right? And then the moment you divide by x squared, you get that. And what do you see? What's wrong? Huh? This, 1 over x squared. This is wrong. What's wrong with this?
Can't have a 0 in the denominator.
Yeah, you can't have 0 in the denominator. X equal to 0 is a singular point of this coefficient, right? And because of that, this mathematical theorem of existence and uniqueness cannot be applied. And in fact, if you try to solve it using this, you fail. You're not allowed to modify these values freely. Now, so to advance this idea further, let me talk about the following idea. This is an important definition. Definition. If a second order differential equation is put into the form y double prime plus px sorry, let me use capital P for the future reference. Capital Px y prime plus capital Qx y equal to 0. If a second order, I should say homogeneous. And P of x and Q of x are continuous at x equal to a. Continuous also contains the definition that it has to be defined. So, in other words, P of A should be defined and Q of A should be defined. Okay? Then we say x equal to A. Sorry, since this part is important, we write it. X equal to A is a regular ordinary. So ordinary is an ordinary point of the differential equation. Okay. Now, then second definition. Second definition is definition 2. Definition 2. If x equal to a is not ordinary, we call it singular. So in other words, opposite of ordinary is singular. So for a given differential equation, a value of x could either be ordinary or singular. In most cases, the values are ordinary and you have just finitely many singular, although you could have some sick example where you have many singular points. But we don't even consider that. Let me see. So let's look at this definition. Going back, if I rewrite this equation as y double prime minus 1 over x squared y equal to 0, the only value of x that causes a headache is x equal to 0, right? So x equal to 0 is called what? Singular point of this differential equation. And every other value, say x equal to 1, x equal to negative 1, whatever you call it, those are called ordinary. Okay. Ordinary. Now, why is ordinary important? That's because as long as it's ordinary, then you can put that as your starting point. So for this equation, if you chose a value of y1 and y prime of 1 as some value, then because x equal to 1 is an ordinary point, this differential equation will have a solution. Okay? Now, there will be, so there's an existence of a solution, and the solution is unique. So it means we can kind of approach this in a nicer way. Okay. So that's the important distinction. There's the ordinary and singular. And when I give you a differential equation, you should be able to categorize where a given point is ordinary or singular, which is kind of easy. All you have to do is divide by whatever coefficient y double prime has. And once you have these functions, just investigate whether it becomes undefined at those points or not. If it's undefined, that's singular. If it's defined, then it's ordinary. Okay? Any questions? All right. If not, now let me show you then how we can solve this differential equation. The first approach is the following. The first approach is to say y is equal to sigma of an. Instead of putting x to the n, you might recall from calculus 2 that there was this thing called Maclaurin series and there was the Taylor series. And Taylor series was an expanded version of the Maclaurin series, where you don't expand at a given point, but you don't expand at 0, but you write down the power series centered at some value a. Right? So in that spirit, we can do, for example, an x minus 1 to the n, with n equals to 0 to infinity. And because x equal to 1 is a singular point now, it's an ordinary point now, then it's possible to plug this in to the differential equation and solve. So that's one approach. Okay? So that's I'll say approach 1. Now, second approach is so this will always work as long as this point is chosen as ordinary. Now, the second one is something that doesn't always work, but this guy named Frobenius investigated this type of solution. So he was looking for like x to the r multiplied to this, where r is usually a fraction or a negative number. In that case, even if you multiply this to inside, you will recognize that that's different from any power series. Okay? So he thought, Frobenius thought about possible solutions of this form, and he realized this doesn't always work, and he categorized the singular points in two categories. There's a regular singular point where this does work, and irregular singularity where this doesn't work. And I'll talk about that in a separate approach. So these will be the type of approach that we will do for these type of differential.